are Amanda, Lindsay, Austin, Jaron, Toussaint, and Edward. No arguments? Okay. I don't know, Diksha, somebody like that asked about doing homework problems. Okay, Cassie. So I actually have a couple problems here that I put in here. Hopefully we don't take too much time on this. These were the problems that had the lowest overall scores from the last two assignments. So the first one here, a sledgehammer of mass 1.9 kilograms falls and hits a piling and drives the piling into the ground. And so we have the question number one is how much energy does the sledgehammer have just before it hits the piling? And then how much force does the piling have while it's driving? I thought I had it so you could see. Did it flash up and disappear, or was I just wrong? Okay. So what's the first thing I should do in solving the problem?
Draw a picture.
Draw a picture. So I'm going to draw my picture. I will have my object up here, that's my sledgehammer, that has a Y initial of 1.3 meters. No, this is from homework that was due on Monday. This is actually the homework that was originally due on Friday that I moved to Monday. So it has that initial height, and the initial speed is 9.5 meters per second. And then it's going to fall down. So it's going to come down here and end up with Y final. We will assume that's a 0 because it says the height initial and doesn't say the height final. We must assume the initial height was given with respect to the final height. And we don't know the speed there. And then there's going to be a third part of the problem. The third part of the problem is going to be then that drives the spike downward. So it's going to end up down here at Y, Y extra final. I'll put YZ equals minus 0.12 meters. And it will have driven this spike down into the ground that distance of 1.2 meters. So there's the full picture. Now for the work. For the first part, how much energy in joules does the sledgehammer have just before striking the piling? What ideas go through your head if you're asked to find the energy at some point? Potential energy and kinetic energy. I said if we're going to solve an energy problem, we always should draw the picture first. What was the second step? Identify the energies at each state. So in this case, I'm going to have kinetic energy initial is 1/2 mass times V initial squared. Potential energy initial is equal to mg Y initial. Kinetic energy final is equal to 1/2 mv final squared. Potential energy final is equal to mgy final, which was 0. And I'm going to stop there because part A only goes between those two places. After I've identified those, the next step is really, really important. What's the next step? Identify if there are any non-conservative forces. So in part A, where the hammer is dropping through air, remembering our caveat from long ago that we ignore air resistance unless explicitly told to treat it, is there any non-conservative force? No. So if there's no non-conservative force, then work non-conservative must be equal to 0, and work non-conservative is equal to the change in energy. So that means the energy doesn't change from the beginning to the end. Now, since I'm only asked to find the ending energy, and I know now that the energy doesn't change from the beginning to the end, then I know that energy final is just equal to energy initial. And I'm not even going to waste my time calculating things like what the speed is just before it hits. I'm just going to take this relationship and say, well, the energy initial is 1/2 my mass times speed initial squared plus mass times g times y initial. And I just put my values in. 1/2 the mass, 1.9 kilograms, times the initial speed, 9.5 meters per second, quantity squared, plus 1.9 does not start with a 9. I don't have space to put it there either. G is always positive 9.80 meters per second squared. And my y initial was 1.3 meters. So you put that in your calculator, and based on the numbers I have, and I actually brought with me a piece of paper that I did all the calculations on so I don't have to spend time or ask, that was 109.9 joules for my numbers. Now, if this was on a test, you would need to have the correct number of significant figures. So how many significant figures do I have in this answer? 2. So my correct answer here, well, actually, it turns out, as luck would have it, it's 3. Why is it 3? It's still going to be 110 either way. It's just 110 with the 0 significant or not. Why is it 3? Because the 1/2 mv squared is less than 100, and the mgy is less than 100. And when you add those together, then you get over 100. And so the multiplication, each one of those multiplications had 2 digits. Each one was good to the units. And so then when we add them, the answer from the addition is good to the units. So this is correctly 110 joules with this 0 being significant. So I put the decimal point. Now we know it's significant 0. Now part B says how much force in newtons was applied to the piling. Interestingly enough, the website did it wrong. At least with the numbers I had, it marked me right doing it correctly, even though they did it wrong. But let's think about this. When it's driving in the piling, what's happening? I have energy transfer. I'm going to convert all of that energy I had, which was kinetic energy at the time of impact, into work driving the piling in. But the part where the book, or not the book, the website, made a mistake is the mass is also going to fall that distance of 0.13 or 0.12 meters. And if the mass falls that distance of 0.12 meters, there's also going to be work associated with that. And the website didn't take that into account. It just pretended that, it, let's say, bounced off or something. If it bounced off, it would have had kinetic energy, wouldn't have transferred all of it. Their answer can't be defended, okay? But they forgot about that part. So I'm going to do it correctly instead of incorrectly. So doing it correctly, I have work non-conservative. When I'm driving that piling in, I have the force of the earth resisting the piling going through it. That's non-conservative. It's not going to give me back the energy. And so that's going to have a work non-conservative. So I have to calculate the work non-conservative. What's our method of calculating non-conservative work? Work is equal to force times distance. Now, what direction is the force trying to keep the piling from going through the ground? Up. What direction is the piling moving? Down. So is that going to be a positive or a negative work? Negative. So my work is going to be equal to minus the force of the piling times the distance it moves. Now I put a dot here, but I didn't put vector signs, so that means it just means multiplication. If I put vector signs in a dot, I wouldn't have had the minus sign, because the dot product, including the directions, is what gave us the minus sign. It's always something we have to pay attention to. So my work non-conservative is that. I don't know its value from this equation, but I know that's an equation that relates the non-conservative work to the force. Then we go to the last step of a work energy problem again, using work non-conservative is equal to the change in kinetic energy plus change in, I'm sorry, different textbooks, different symbols, change in potential energy. And so that's where I'm going to have the change in kinetic energy is just going to equal this 109.9 joules. Except for it's going to be a loss because it's going to end with 0 kinetic energy and it started with 109.9. So that's going to be minus 109.9 joules. Just took that right there for the change in kinetic energy, 0 minus that. Minus mass g times that distance. Why minus? Because the potential energy is going to be lower in the end, so it'll be at minus mgd at the end. It starts at 0. On this side, minus fp times d. Well, if I want to find fp, first thing you know, they're all negatives. If they're all negatives, I can just multiply by minus 1 and make them all positives.
Why was the mgd negative? Sorry, I messed up.
Okay, because change in potential energy, just like change in kinetic energy, was kinetic energy final minus kinetic energy. Okay, I can't use final because final was that one up there. But let's say 2 minus 1. This one here is going to end at stop. And this one here was the 109.9 joules. And likewise, change in potential energy 2 minus potential energy 1. This one here was the 0. And this one is mg times, and it went down to minus d for its height. Okay, divide everything by d, and I end up with the force, the piling average is 109.9 joules divided by my distance of 0.12 meters, plus the d's here will cancel, my mg 1.9 kilograms times 9.80 meters per second squared. This second term is somewhere around, 18 joules or so. And so that's the part that the text or the website forgot. So the correct answer was, for my numbers, 934.8 newtons. The one that the text or the website had was actually green. The website had 916.2 newtons. It marked either one correct, but this here would be the correct answer, and it had the other one for its answer. Okay, so going through the problem, it was, like I said in class a week ago today. We just go through those steps I gave you of drawing the picture, identifying the energy at each important place, determining if there's work non-conservative. If there is, find its value, and then use this form of the work-energy relation. Any questions? Yeah, Diksha.
So if the work or the energy was conservative, you just not.
If
the same thing to solve if it's conservative.
If it's conservative, then the work non-conservative is 0. So you have what we had for part A. But if it's non-conservative, then you have something that's not 0 there. So I used the same equation in both cases. It's just here it wasn't 0, here it was 0. Other questions? Okay, let's look at the next one. The next one was the pyramid one. You have a historical problem, building of the pyramids. And Michael, I did figure out why we had a different number. So you'll see here in the solution. It starts with something simple. It gives us the important numbers, the area of a side, which we are not going to use, the height, and the mass. And then things about the number of workers, how many years it took, how long per day we expect, and how many days per year we expect they work. It's good to know that even the slaves building the pyramids got themselves a good month and a half off of work. Although probably that would be take away Sundays, or, you know, if they were Hebrews, probably take away Saturdays. Okay, so we have all of that information. Here's a pretty picture. And since we're not doing a calculus-based class for most people here, it tells us the center of mass is at 1/4 the height of the pyramid. For calculus-based people, I worked it out, at least with one, because it's not a hard calculation. It just requires you to do an integral. So, assuming that the potential energy of gravity at the ground has 0 value, what's the total potential energy? Well, that's very straightforward. What's the equation for gravitational potential energy? It's mgh, and so that's going to be the mass, 7 times 10 to the 9th kilograms, times g, 9.80 meters per second squared. And then for the height, they said take the total height and divide by 4. And you multiply that together, and I think it's 2.5. Yeah, 2.5. How many significant digits do I have in this number? 1, just 1. Now, I told you with Expert TA, they grade off of 4. So I would keep the 2.5 and not put in the correct rounding for this, just to make sure we're on our toes. What's the correct rounding of this number? 2. 2 times 10 to the 12. But if you put that in, there's a good chance it would have marked you wrong because they're not paying attention to significant figures. Okay, so that was easy enough. Part 2, only a small fraction of workers lifted blocks. Most were involved in support services such as building ramps, bringing food and water, I love those people, hauling blocks to the site. Calculate the percent efficiency of the workers who did the lifting, assuming that there were 1,000 who actually lifted blocks. So we're going to say, okay, so 1,000 people did the lifting, and they consumed 300 kilocalories per hour for the 12 hours they were lifting. So we can say for part B, the energy consumed per person per day is equal to that 300 kilocalories per hour. Wow, that's... KCAL was the radio station I listened to when I was in college. Times the 12 hours they were working. So that's 3,600 kilocalories. Now that's a unit of energy. It's not the one we normally deal with, but it's a unit of energy, so I can move on from there if I like, or I can change it into joules. Since I'm going to calculate the percent efficiency, it might be beneficial to convert that to joules since my total energy is already in joules. So if I take that and convert it to joules, I have to use the conversion for kilocalories, which is another term for a dietary calorie, and joules, which is 1 kilocalorie is equal to 4186 joules. I know our textbook says 4184, and I can't understand why we have confusion on the number. And so you just take the 3600 kilocalories times 4186 joules per kilocalorie, and you get a reasonably large number. That number is, on this sheet, 15 million. I'm just going to put 1.51 times 10 to the 7th joules. If you list it in joules, it sounds like you're eating an enormous amount of energy. And it actually is. I've been sitting eating peanut M&Ms, don't tell my wife. You know, just a few of those is enough to keep me going probably all day if I were to really be honest. So that's how much energy the people are consuming per day. And now we need to figure out how much work they're doing against gravity per day. So the work they're doing per day against gravity is going to be equal to the potential energy of the entire structure divided by the number of days that work was done on it. So that would be 20 years, 330 days per year. And then per person, so we need to divide by the number of people actually doing the lifting. $20 times 330 times 1,000. That would be 6.6 times 10 to the 3, 4, 5, 6. And that number is it turns out that 6s aren't written like a 2. 2 times 33 is 66. Y'all recognize? Yeah. That was a mistake on my part, hidden writing. So it comes out to be 3.79 times 10 to the 5th joules is the work done per day, per person. So for the efficiency, the work done per person per day divided by the energy consumed per person per day, multiplied by 100%, and you have 2.52%. And once again, we're really only good to one significant digit, but putting out more digits there. That's how efficient the workers were at converting food energy into building a building and storing it in gravitational potential energy. Not very efficient, right? Well, that's because, number one, there was a lot of work done that's not just vertical lifting. Like if I take the block from here and carry it over to here, I'm going to expend a lot of energy, even though there was no mechanical work done. Number two is, even when you're sleeping, your body is using energy. Your brain is using energy, your heart, whatever. Everything's using energy. So it's not an astoundingly low percentage when you think about everything involved. And then finally, part C. Part C asks us about the consumption of food. It says 5% of their energy comes from protein, 60% from carbohydrates, and 35% from fat. And so, and this is Michael, is where we did it differently and got a different number. The way to start is say, okay, if that's the case, if 5% of all of their energy came from protein, then from protein I had to have, for a single day, this many calories, right? Per person. So if I have 3,600 calories per person per day, and it was 5% that came from protein, then I'll multiply that by 0.05, the 5%, and that will tell me how many kilocalories I have coming from protein. So if I take that, multiply by 0.05, I'm going to have 180 kilocalories from protein. Protein. That was right. And then for carbohydrates, that was 60%. So 60% of 3,600 is, I think it's 2,160, but I'm going to check my numbers. Yeah, 2,160. And finally, from fat, I have 1,260 kilocalories. Now that I know the energy from each one, I use the energy per mass to find the mass. So the mass for protein is going to be equal to the energy from protein divided by the energy per mass for protein. So that would be 180 kilocalories divided by 4.1 kilocalories per gram. And so that's a number in the ballpark of 43.9 grams. So each worker needs 43.9 grams of protein. And for carbs, 160 kilocalories divided by that same 4.1 kilocalories per gram. So 526.8 grams of carbohydrates, and the mass from fat is 1260 divided by 9.3. Equals 135.5 grams of fat. So that's the total mass that a single person needs to eat in a day if I add it up. So I add all of these up. 9, 8, and 5 is 2. And I actually add, it turns out to be 706.2 grams. That's how much mass each person needs to eat. That's a lot of mass, actually. And then if we want to take this and say, okay, we had 20,000 total workers, and we're saying each one used the same, the mass total is 20,000 workers times that amount. I convert it to kilograms because your answer had to be in kilograms. 14,000 kilograms of food consumed per day. Or, a little over 7 metric tons per day. Pretty extensive amount of food required to build those pyramids. Now, this was not a typical physics problem. It was one to help us put things in context. To put the energy that we're talking about in physics class in context with energy that we consume and expel in our daily lives. Any questions about the problem? None? Okay. It was the most missed, right? I chose the one that would potentially have the most confusion about it. All right. To momentum. Momentum, remember, is mass times velocity. Momentum is conserved if, according to Newton's second law, if delta P is 0, because that's what conserved means, what condition would make delta P 0 according to Newton's second law? Okay, so P conserved if force net equals 0. There's actually another or. What other condition would conserve momentum? If there's no time. Well, okay, there's no such thing as no time, right? But in something like a collision, usually the time for the collision is very, very short. And what's really important is the product of those two, the time and the force external. The internal forces, the forces within the system, add up to 0, so only externals matter. And so if the external force multiplied by the time of the collision is very small, then we can approximate that momentum was conserved. The textbook points out the only case where we can truly have momentum conserved is in particle collisions. Like we fire an electron at a proton. Although if you take the entire universe as your system, you always are going to have momentum conserved in the entire universe. But we can't do any work with the entire universe, so that's not very useful. We usually approximate that the Earth is stationary. And how's the Earth stationary? It's definitely not stationary. The Earth is orbiting the Sun. The Sun is orbiting the center of the Milky Way galaxy. The Milky Way galaxy is moving about as it interacts with things like the Andromeda galaxy, the large and small Magellanic Clouds, and of course, the Sagittarius dwarf galaxy that is currently within the Milky Way galaxy. So all of these things are moving. We can't say that the Earth is stationary. but we treat it as a stationary reference frame because it's approximate. So in our problems, once again, unless specifically we have information otherwise, we will treat the Earth as stationary. So for our problems with collisions, we treat the Earth as stationary. If I have a car hitting another car, I'll take the two cars as my system and say, okay, I'm looking at them from the Earth is stationary, I have the two cars hitting each other. As long as the external forces on the cars add up to 0, I'm good for momentum conservation. And in fact, I really only care about momentum in the direction they're moving. For a one-dimensional problem, I'll just say forward, backward direction. If we get to the last problem I've set up for today, we'll be doing a one-dimensional car collision problem. One-dimensional, I'm only going to care about forces that are in the direction of the cars moving. Yes, there's a force of gravity down. Yes, there's a force normal up. Surprisingly enough, since the cars are not accelerating in the vertical direction, that is, their speed is not increasing in the upward direction as they fly up into space, the sum of the forces is 0, so the net force of vertical direction is 0. Momentum is conserved in the vertical direction, it just stays 0. Horizontal is what I care about. So we need to look at our systems and be careful what we have in our system and apply only external forces to that system when we're calculating if momentum is conserved or not. Now, momentum is used in a lot of situations. Here's one that you may not think about. You have something like a rocket. When a rocket goes in space, okay, I know we did the rocket problem yesterday in class for the people in Physics 251. Let us assume that our rockets are like home play rockets, where you burn all the fuel in like half a second and then it's just gliding for the rest of its trajectory. You have this rocket that's gliding. What do we call the trajectory, the path taken, its shape, for an object just flying through space with no air resistance or anything? What do we call that? I'll give you a clue. It's not a circle, but I'm looking for a shape, something like that. Yeah, we say it has a parabolic arc. But if I have something like a rocket, that rocket could tumble. The rocket could be going like this. If it's going like this, what part of the rocket is doing a parabola? The answer is the center of mass. The center of mass is a term that means the average position of the mass. So to calculate the center of mass, we do it just like we do something like the average score in a test. On our first exam, in case you're curious, the average score in the first exam was 83.69% or something like that. Basically 84%. How do we get that average? We take every person's score and multiply it by the number of people that got that score. So let's say, I know, 2 people got 96%. So we would say, okay, so we have 2 people times 96, 1 times 97, and go on through all of them. We add them all up. And yes, obviously I'm not saying the lowest scores, I'm saying the highest scores, because it's not as fun to say, hey, that's me, when it's the lowest score. And then we divide by the total number of test takers. That's how we find the average for the score on a test. Well, we do the exact same thing to find the average position for mass, to find the center of mass. So this equation here is showing you how we find that. So to put things real simply, let's say we have a system that consists of 2 pieces. Block 1 and block 2. And block 1 is at x equals 3 meters, and block 2 is at x equals 5 meters. Block 1 has mass of 10 kilograms, and block 2 has mass of 5 kilograms. If I want to find the center of mass for this, I just put it into that calculation. So I do x center of mass is equal to mass 1 times position 1 plus mass 2 times position 2 all over the sum of the masses. The masses are the weighting factors, just like the number of people with the score was the weighting factor for the scores in the test. And then the x's would be like the scores in the test. Put our numbers in, that would be 10 kilograms times 3 meters plus 5 kilograms times 5 meters divided by 10 kilograms plus 5 kilograms. If you add that up, on the top I have 55, on the bottom I have 15. And that would be 11 over 3. So that would be 3.6 repeating meters. That's how you find the center of mass. And so if I had these tied together with a rigid massless rod, and that was flying through the air, so I take this rigid massless rod that's 2 meters long with these masses at the end, and I throw it through the air. Can you catch this and not get your eye poked out, Zach? Yeah. Okay. So I throw this to Zach. It's going through the air, going around. The center of mass did the perfect parabolic arc. And then the rest was orbiting around that. And yeah, I just wanted to make sure. I went through the tennis ball to a girl, and she just stood there. Conk. So from now on, I ask people, rather than throwing and letting them get hit, and say, "Ow, you hurt me." I said a girl to a student. She happened to be a girl, but anyone could sit there and let it hit them in the head. It's not I don't think, a feminine trait. So, yeah.
And that's true for any objects in, like,
any object, if you ignore air resistance, the center of mass is going to be doing the parabolic arc. Yeah. And you can also treat the force of gravity as if it's acting at the center of mass. Now, this becomes untrue in unique situations, like if you have a non-uniform object that's big enough that the acceleration of gravity is different in different parts of the object. But as long as you don't have a non-uniform object big enough that the acceleration of gravity is different in different parts of the object, then you can still treat it like the force of gravity is acting at the center of mass. Technically, you have the center of gravity for where gravity acts, and the center of mass for the arc. But the fact is, they're going to be the same for any practical case. We're not building huge things where it's going to be different. So we have this center of mass idea, and you might be wondering why it shows up here. It shows up here because when you're working on problems with collisions, sometimes it's very convenient to work a problem in the center of mass reference frame. So that is, if I have two cars colliding, I might choose my reference frame so my reference frame is moving, but in that reference frame, each car is coming toward each other at the same momentum. Not the same speed, because they might have different masses. But they have the same momentum going in opposite directions, so the total momentum is 0. That makes life a little easier sometimes because you have that total momentum is 0 term. And so understanding how to find the center of mass is an important first step. How do you find the speed of the center of mass? Well, to find the speed of the center of mass, you just divide everything by delta t. So the speed of the center of mass is equal to the speed of object 1 times mass 1 plus the speed of object 2 times mass 2. It's the same calculation, just replace x with v. Okay, kind of a non sequitur, it seems, but this is where it's in the textbook first. Figure I better put it in rather than forget, and then later on say, "No, we studied this." Some applications. In particle physics, last semester, spring semester last year, I taught a class in particle physics to my physics major. And so we were studying things like what's happening when you collide an electron with another electron. It's a simple particle interaction. And our fundamental rules were conservation of momentum and energy. Those were our fundamental rules, and everything else came out of that. Now, for that, we were using 3-dimensional collisions, not 1-dimensional. When you do three-dimensional collisions, well, then you have conservation of momentum in all three directions. Kinetic energy is a scalar, so it doesn't have direction. So that actually gives you four conditions. And so those are what sets up how you do those calculations. And of course, your energy isn't just kinetic energy. You have the rest energy, the mc squared. And it gets more complicated, as you might guess. So that's what this left picture is. The right picture is much more rubber meets the road, in a very literal sense. When you have collisions between automobiles, oftentimes there are questions of who's at fault, whose insurance is going to pay. And those questions then require us to come back and recreate the situation, like who was driving too fast or too slow or whatever. And the best way of determining that, since people invariably don't know, and even if they did, they're probably going to fudge it in their favor. You know, oh, I couldn't have been going more than 5 miles an hour over the speed limit. They go back and they do things like they measure the lengths of the skid marks and the paths they take, and then they apply the physics that we are learning right here to determine, okay, so what really happened in the collision? So I got a few more slides before I get to my problem. Because there are two fundamental types of collisions, like we learned about in lab yesterday. First, the elastic collision. Elastic collisions involve conservative forces that give the energy back as kinetic energy. So for our labs yesterday, that force was the magnetic force. It's a conservative force. As they got closer together, we had energy stored in that magnetic force. So you saw the kinetic energy drop during the collision. But then it returned the energy as kinetic energy, and so it came back up. In the case of an elastic collision, we have two fundamental equations. Now, once again, I'm doing one-dimensional, so it's only going to be one equation for momentum. We have conservation of momentum and conservation of kinetic energy. Now, remember, kinetic energy isn't always conserved. Total energy is always conserved. But an elastic collision is a special case where kinetic energy was conserved. So I have those two conditions. Let's look at the equations, because the equations come out to be a little different than you might think. Momentum conservation. Notice the symbols used by the textbook. It uses a prime, that's what we call the little single quote afterward, for things that are after the collision, and unprimed for before. So for conservation of momentum, before the collision and after the collision, I would write this as, P total is equal to P total prime using that kind of notation. Or more specifically, mass 1 V1 plus mass 2 V2 is equal to mass 1 V1 prime plus mass 2 V2 prime. I am sure there is no one shocked by that. We rewrite this in a way that may surprise you, may seem like it's a waste of time. We rewrite it by bringing the masses together. So I'm going to bring this over here, bring this over here. So I have to subtract the two that have arrows taking them away so I can move them to the other side of the equal sign. Then I can factor out the masses, so I have M1 times V1 minus V1 prime on the left side equals M2 times V2 prime minus V2. Notice the V2 prime is positive because that's the one that I left alone. And so that's the equation we use for conservation of momentum in collisions. Whether it's elastic or inelastic, that's the equation I'm going to be looking at. Like I said, it might seem like it was a little unnecessary math until you do the next part, the kinetic energy part. Our kinetic energy conservation says kinetic energy equals kinetic energy prime. What's the equation for kinetic energy? 1/2 mv squared. I'm going to have squares. That complicates things. So I will have 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 V1 prime squared plus 1/2 M2 V2 prime squared. Now the first thing anyone should see here is I have a 1/2 in every term. Only a stubborn fool would keep those 1/2s. Everyone else would multiply by 2 and get rid of all of those 1/2s. And then we do the same thing we did with momentum. We bring the mass 1 terms together and the mass 2 terms together. So we have factoring m1 times v1 squared minus v1 prime squared equals m2 times v2 prime squared minus v2 squared. Okay, that does look maybe a little simpler, but it still seems a little out of place until I take my next step. I can take something squared minus something squared and decompose it into v1 minus v1 prime times v1 plus v1 prime. Right? I didn't learn until I came to Nebraska that term FOIL. I just learned multiply them. But when you multiply these, you have v1 squared, then v1 times v1 prime minus v1 prime times v1. Those add out to 0. And then minus v1 prime squared. So it's the same thing. Whoops, didn't need. So there I've expanded it. And now people are going to look at me and probably think Richard the Fool just made more work for himself. But look at the box in red. M1 times V1 minus V1 prime. That's this right here. That's equal to M2 times V2 prime minus V2. That's that there. So that means that these two things are going to cancel out because they're equal to each other. And I'm left with a much simpler equation. V1 plus V1 prime equals V2 prime plus V2. And so that's the second equation I use for conservation of kinetic energy. So when I'm working a problem that involves conservation of kinetic energy, i.e. an elastic collision problem, I have two equations to solve for. How many unknowns can you solve for if you have two equations? 2. So I have to know all but 2 of the variables. What are the variables? Mass 1, mass 2, speed 1 initial, speed 2 initial, speed 1 final, speed 2 final. So there's a total of 6 variables. I have to know 4 of them, and then with these 2 equations I can solve for the last 2. If I have 5 of them, I can solve with only 1 equation. If all of my unknowns are v's, I'm clearly going to use just this one. If I have a mass involved, then I'm going to use this one. So those are the equations we use to solve elastic collision problems. I clearly won't have a chance to do the last problem, but I will have a chance to have the 2 clicker questions and show you this. Because in elastic collisions, we are going to focus on the perfectly or completely inelastic. So perfectly, if it's perfectly inelastic, they stick together. And so I replace that conservation kinetic energy equation with V1 prime equals V2 prime. That's a real easy equation. So it's easier to do the perfectly inelastic collisions because they stick together. The second equation is very simple. Okay, so for our clicker questions, clicker question number 1, which you can answer now. In which case is momentum conserved? Only elastic collisions, only inelastic, in both, or in neither? Okay, we had 3, 2, and 17. The 17 were right. Momentum was conserved in all of our collisions. And finally, for our last clicker question, in which case is kinetic energy conserved? And it's the same options. Okay, so we had 19, 0, 21. And only elastic was correct because that's what we mean by elastic collision. A collision in which kinetic energy is conserved. All right, have a great long weekend. There obviously won't be a Flip Friday because we don't have class on Friday. There will be a homework assignment due Monday. I'll see you then. You know, I haven't looked at the schedule that far in advance, but it's likely that that's what I have scheduled.